Alright, I know why you clicked on this video. Dismantling our solar system seems like the ultimate act of eco-terrorism, and to put it mildly, a bad idea. Why would we do such a thing? What possible benefit would eliminating all naturally occurring astral bodies around the sun bring to us? Where would we live if there weren't any planets? Well, contrary to how this video is started, this idea began not with defending its enacting, but with a need to begin this process. The hard truth of life on current-day Earth is that human beings take resources to live. All life uses resources and produces waste, whether it be biological or industrial. So how am I going to use that argument to convince you that decimating our solar system is a good idea? Welcome back to Serious Science, and this is why humanity should disassemble our solar system. To begin, I'm no monster. I grew up gazing slack-jawed at images taken around or on other worlds. The desolate dunes of Mars may be lifeless, but are still beautiful, and Saturn's rings may be filled with cold, dead ice, but still serve as the crown jewel of the solar system. But the fact of the matter is that most objects orbiting the sun are tiny rocks with no hope of ever supporting life. Let's look at it this way. How many planets are there in the solar system? 8? 9 if you're a die-hard Pluto fan. Wrong. There are tens of thousands of estimated planets orbiting our sun. How have we never heard of them before? Well, in all honesty, the vast majority of them are dwarf planets or rocky bodies teetering on the edge of being classified as such, and almost all of these are uninteresting balls of raw material in the frozen depths of space. There are some interesting ones, however, if only for their striking appearances, such as Gong Gong, a red-tinted sphere with a thin methane atmosphere located in the Kuiper Belt, or Eris, a world more massive than Pluto with an equally large moon joining it located beyond the orbit of Neptune. But one fact remains. Most of what orbits the sun is lifeless and uncolonizable. These asteroids and dwarf planets have too little gravity for humans to live on without experiencing dangerous health risks and hold very little promise for generating life. They are, however, packed full of valuable, rare, and useful materials. Rubies, sapphires, diamonds, gold, platinum, and even opal have been discovered inside of asteroids or on the surface of other nearby worlds. Any element we hold valuable here on Earth is in near infinite supply outside of our gravity well. This isn't even mentioning the vast amounts of less valuable but still sought-after resources we use to create mundane items, such as iron, silicate, hydrogen, methane, helium, and dozens of other elements we use every day to make enlightened life on Earth possible. And here we face our first pressure to expand outwards in search of resources. Earth is currently the only known planet on all of creation that supports life, making it essentially a massive preserve. It is, however, the only world we can currently exploit in order to live in a technologically advanced society. The more time we spend here on Earth growing our population, the more resources we will need to take from our Earth in order to survive. Hundreds of years ago, exploiting the planet meant tearing up vegetation to create farmland for growing plants that already existed on the planet in the first place. Today it means supply chains all burning fuels to provide food, materials, electricity, and expensive space and ground-based communication systems to every person possible. In order to save our own world from total consumption, we will need to turn to others, and the good news is that most of the planets around us are already in a state far worse than if we had polluted and nuked every inch of them. So, where would we begin? If we want to start harvesting worlds, we will need to take into account not only their present benefit to us, but their future ones as well. For example, we would most likely not rip apart Mars or Venus for their raw materials, as these two worlds are prime candidates for terraformation, and may prove better uses as next-generation Earths. But planets such as Mercury or our gas giants show little promise for colonizing, as creating Earth-like conditions on or around them would be more trouble than they're worth. Though these planets are still vast wells of raw materials useful in creating not only the systems to aid in terraforming others, but all of the cities, vehicles, and infrastructures on our new worlds. Starting down the line of planets that orbit our star is Mercury. I've actually done a past video talking about turning the entirety of Mercury into a Dyson swarm around our sun, as it is rich in metals suitable for construction, and is in close proximity to the star we would want to surround. Check it out here. But I will spend a little time talking about the actual specifics of disassembling planets. It's easy to say that a world could serve us better as a quintillion tons of steel in use all over the galaxy, but how would we feasibly dismantle one? Let's start with the rocky ones, beginning with the easiest of these worlds, asteroids. These boring chunks of protoplanetary matter would be quite simple to mine. Ships could reach them using little fuel, as there wouldn't be a massive gravity well they would need to escape in order to ship these resources elsewhere. The microgravity here would also play a major role in separating out these elements from one another, as a mining rig could be anchored to a rich section of an asteroid, sending what it extracts up into extremely efficient centrifuges. These spinning drums would be able to separate elements in accordance with their masses, either through raw chunky collisions and eventual settling, or through a combination of a centrifuge and a molten furnace. These materials could be mined from asteroids with incredible ease using either a blade of lasers inside of confined material collecting spaces or through the more common form of drilling. Asteroids are also unique in their composition, as many of them have such little gravity that they are essentially large balls of loosely packed gravel barely held together. In other words, extremely easy to separate and sort. These asteroids could even be moved around the solar system in order to send them to larger facilities closer to the Sun and our homeworld. The farther we go from our Sun, the slower objects will orbit. This means that even the slightest amount of added momentum will drastically change the orbits of such distant asteroids, making a transfer from Kuiper Belt or Oort cloud to the inner system a cheap and quick expenditure of fuel. All that would need to be done would be to rendezvous with the asteroid as it shot past the Sun hundreds of years later, and harvest all we could before it swings back out into deep space. But this could be simplified even further. Why send a rock half filled with precious metals home instead of refining everything we want from them and sending these materials packaged up nice and neat in a similar fashion? Ships headed out beyond Neptune may be equipped with onboard smelting and refining facilities in order to get the most bang for their buck, so to speak. This is similar to how over 650 people all across the planet are getting the most bang for their bucks by subscribing. Yep, still doing it. Now let's move on to the fun ones, dwarf planets. These worlds make up the majority of the objects we would call planets in our solar system, and are all far smaller than Pluto. Pluto has a surface gravity 1/15th the strength of our own planet, meaning that a 100-pound weight on Earth would only weigh about 7 pounds on Pluto. This means we can extract far more materials using smaller rockets than if we were exporting our own planet's resources. Pluto's escape velocity, or the speed at which an object must be traveling in order to escape the planet's orbital gravity well, is only about 2,800 miles per hour. This may sound like a large amount of speed we will need to propel a rocket to in order to make a return trip from orbit, but this number pales in comparison to the 25,000 miles per hour we need to travel at in order to escape Earth's orbit. And all of these numbers are describing what we would need in order to ship materials off of the largest of our system's dwarf planets. The smallest currently known dwarf planet is Hygeia, which has a diameter of only about 296 miles, and an escape velocity of about 519 miles per hour, the speed at which most intercontinental flights travel at inside of our own atmosphere. But this isn't to say that we will be giving it another cold shoulder to Pluto in our expansion efforts. If interstellar flights become commonplace, we may want more than just a departure and arrival destination. If a ship expends a large amount of fuel escaping both Earth and the Sun's gravity well, it may be prudent to refuel at a distant location before making the leap into interstellar space. A location Pluto would serve well. The thin atmosphere of Pluto is a mixture of primarily methane and nitrogen, which in the incredibly chilly conditions form stable hydrocarbons we could refine into rocket fuel. Pluto may become a base camp for interstellar travelers to refuel at and stretch their legs on the last alien world before the true final frontier. But the other dwarf planets? They don't have enough gravity for humans to live on without our bodies wasting away, and many are so loosely packed that spinning them up to generate additional gravity would simply rip them apart. Not a bad idea if we start looking at them as resource wells. The smaller of these planets could be mined in fashions similar to what we would use on asteroids, albeit needing just a bit more fuel in order to depart. As for the other thousands, we could use methods that have already been planned for constructing habitats on our own moon. The moon has high concentrations of aluminum, silicon, and titanium, some of the most used materials in manufacturing. Planned missions to our moon to utilize these materials consist of regolith sifting crawlers and stationary smelting and refining facilities. Essentially, large crawlers would sift through the regolith, or in simpler terms, moon dirt, and sort the collected materials using our previously mentioned asteroid centrifuges. These metals would be taken back to base to be smelted down and shaped into construction pieces used in creating inhabitable surface bases, rocket departure and landing stations, and even fuel for those rockets. We could employ similar machines to refine and mine the surfaces of other dwarf planets that would enjoy gravity wells far smaller than even our own moons. These refined materials could either be converted into useful surface infrastructure if we wanted to settle these worlds, or be sent in their entirety to Earth and other worlds that need additional materials. But what about the main 8, the actual planets recognized as such that we share our solar system with? First of all, the entire point of decimating asteroids and uninteresting dwarf planets is to spare Earth from the same fate, as we will need resources as we expand, and those resources will have to come from somewhere. So dismantling Earth will probably be off the table, unless of course our homeworld is under a peril we cannot divert or ward off, in which case the exporting and preserving of all we can and sending it out into the void would be the most amenable option. Perhaps that could be a topic for a future video. I've already discussed what Mercury could be used for, especially as we have no current idea of how we would live on such a world, or even why we would want to. If the goal is to get as close to our sun as possible, the task would be far easily achieved through the use of smaller orbital crafts and stations that could be constructed from the ground up with heat dispersion in mind. Whatever we wanted to send down to the surface of Mercury would need to not only deal with these same heating issues, but would need to be armored against the harsh conditions on the surface, such as static charged regolith, jagged, unyielding terrain, and little room for artificial gravity centrifuges required to keep our bodies and hearts in full working order. Venus, for however unbelievable it may sound, is a better terraformation candidate than Mars. Venus is the closest body in mass to our own world, having about 91% of our surface gravity compared to Mars's 38%. Venus also has an atmosphere, despite it being mostly CO2 and sulfuric acid, both of which could be offloaded for use in other terraforming and industrial projects. But both Venus and Mars lack something essential for creating Earth-like conditions. Neither possesses a protective magnetic field. Without it, any atmosphere or temperature regulation we would introduce would be blasted away by the intense radiation from our sun within a few thousand years. A bad option for anything we would want to make permanent. But we actually have serious plans for creating artificial magnetospheres around planets, none of which would involve changing the interior core of these worlds. Around any orbiting body that exerts an outward gravitational pull exists a number of Lagrange points. These are special areas around worlds where the gravity of the planet and the gravity of their star pull equally. Think of it as a slightly smaller or larger orbit than the planet orbiting the sun, where the orbit around the sun is gently pulled faster or slower by their proximity to the planet. Where objects closer to the sun would orbit it faster, the gravity well of the nearby planet pulls these objects just a bit more than the orbit of the sun does, essentially freezing these objects directly in front of or behind that planet. Whatever we parked in such a spot would be held there forever, if we gave them the ability to make small corrective burns when needed. What does this mean for terraforming? We could place an orbital facility powered by several nuclear reactors that would generate an extremely powerful magnetic field around this Lagrange station. If placed directly between the sun and our prospect planet, it could divert massive amounts of radiation, creating a magnetic umbrella in front of our sun, protecting the planet without it possessing a magnetic field of its own. This facility would not need to be some massive planet-sized disk in order to cover all of a planet. A small station a few miles wide could accomplish this task without blocking out all of our sun's starlight that we may want further down the road for power or heat. But in the case of Venus, we may want to do just that in order to rapidly cool and condense the planet. A micro-thin, multi-thousand-mile wide sheet of reflective aluminum could be placed in Venus's sun-facing Lagrange point, and could be easily manufactured and deployed from any number of worlds. This doesn't mean we won't attempt something similar with Mars sometime in the future, creating a triple planet system of inhabitable worlds for us to colonize. Now we move on to what will be our second greatest resource wells in the solar system, the outer gas and ice giants. We've discussed the dismantling of our rocky bodies, but where would we get the fuel for such monumental industrial feats? The outer planets have the solution, as they are made up of primarily rocket fuel. Hydrogen, helium, methane, and organic compounds could all be harvested from the gas and ice giants, fueling millions of reactors, power stations, and rocket engines all across the solar system. Harvesting these resources could be done through a number of ways, from the simplistic diving and resurfacing of ships with open gas nests to blasting their atmospheres with immense lasers, boiling it away from the crushing pressures and gravities of the gas giants for easy collection in space. Such harvests would last millions, if not billions of years, providing humanity with a near-endless supply of fuel to run their empires. Even the moons of these gas giants could be useful. Io, the closest moon around Jupiter, is the most volcanically active world in our solar system, making it a prime spot for thermal power generation. This would be useful as a power source so far from our sun, essentially a miniature star we could harvest for its heat without beaming microwave power all the way from the sun. Titan, a moon around Saturn, is a frigid, methane-rich planet. It is a world whose atmosphere and surface lakes are comprised entirely of easily collectible rocket fuel. The frigid temperatures actually hold their own benefit, as sensitive machinery that operates best at freezing temperatures, such as computers or reactors, could become widespread across this sub-zero oasis. And that may be the end of our discussions, as we have covered dwarf planets, regular planets, and gas giants. But there is one more thing our solar system has that hosts vastly more resources than all of these combined: our own star. I've discussed harvesting our own sun in past videos, such as this one in the connotations, and a common belief is that messing around with what our sun is made of and how much of that stuff it has is probably a one-way ticket to exterminating the solar system and anything within a few light years. But this is far from the truth. As stars age and transform their materials into heavier ones, it loses the ability to produce energy from fusion reactions, causing the star to bloat and eventually explode. If we were to remove select elements from our star, we would be removing the materials that poison our sun and lead to its death. Harvesting the heavier elements from Sol would actually extend its lifetime, creating a near-immortal star for humanity to flourish around, as it has done so for the past 200,000 years, and may do so for trillions of years to come. The sun also makes up about 98% of all the matter in our solar system, and is not entirely comprised of gas. While it is mostly made up of healthy hydrogen and helium, it also contains carbon, sulfur, iron, silicon, and over 61 other chemical elements, all of which are contributing to the eventual death of Sol. Powerful magnetic satellites could suck up these materials in a method called starlifting, being packaged up and sent home for use in things other than the poisoning of our own star. So, we've stripped our solar system for all its usable resources. The sun still shines, and the evaporation of the gas giant still has many millions of years to go until it is complete. Venus, Earth, and Mars shine blue and green under the light of a rejuvenated star, and humanity lives all across our solar system, enjoying wealths of resources beyond belief. What do we do with all this free matter? What wouldn't we do with it? We could build incomprehensibly large colony ships to spread humans to every star within our reach, carrying entire planets' worth of fresh atmospheres for the terraformation of alien worlds. We could build encompassing Dyson spheres around other suns to create multi-layered worlds capable of hosting quadrillions of humans. Or we could even compress the excess matter taken from other worlds into artificial black holes capable of powering our vessels for literal infinite timelines. Humans need resources to live and thrive, and the easiest way to save our own world from total consumption is to take the ones that are dead. The future of our solar system will still be filled with living worlds, but it offers so much more than we could imagine in how it can keep those worlds pure and thriving. Check out the channel's community tab so that you can vote for our next topics. I hope you all enjoyed, and thank you very much for watching.